Okay, so let's get started. We are quite a bit ahead of schedule. So let's see what we want to do this week. So this year we talk about quantum universality following the quantum circuit. But I've said that we want to skip this, so I guess we'll go through this really quick. But anyway, we talk about, so this is the range for end of the range for the midterm, and I guess this is the most interesting part of the first half of the class, the quantum algorithms. So any question on this? Let's give a quick summary. So the quantum algorithm, we talk it in more theoretical form. So we treat it as query algorithms. So we think about some kind of quantum query, which we think about like a sub-algorithm that you can put several of inside your quantum algorithm. And you want to minimize the number of times you run this sub-algorithm. And the cool part, so this is where we start using quantum computing. So the cool part of those quantum queries is that they obey quantum superposition. So so those quantum query has the input register and the record register. And if you put computational basis state in the input register, basically it just write down the output, this function f of x, just like a classical query. But what's really interesting is if you put a superposition in your input register, then you get this entangled output as the output state. So the output state will be entangled between the input register and the output register, like this. So x and tensor f of x plus, so x1 tensor f of x1 plus x2 tensor f of x2. And we have seen several algorithms that this quantum superposition actually gives you a quantum speed up. So we start with the easiest example, that's this George's algorithm. Where you just put a superposition between 0 and 1 in your algorithm, and you are able to learn f of 0 plus f of 1 in just one query. And here we introduce a very important trick, that is phase kickback. So if you have a binary output, then you put a minus state on your record register, then you found out that you can kind of ignore the record register, and your query is just going to put -1 to the f of x on your, it's a global phase, but we ignore the record register, so it's like a phase on the input register. So, so this is a phase, and you kick back to the, so you kick a phase from the record register onto the input register. And in this form, it signifies what happens if you put 0 plus 1 on your input register. So if 0 plus 1 on your input register, then the oracle will just make a distinction where f of x0 or equal to f of 1, because there will be a relative phase between the 0 input 2 and the 1 input 2. So that's George's algorithm, and then we see several other algorithms. George-Josa, okay, let's scroll this, it's annoying. So George-Josa algorithm generalize the input to several qubits. And you still solve this by one query, although you need to do some classical post-processing. And then there is Bernstein-Vazirani, it's the same algorithm, but now your function has a very special promise that the promise that your f of x equal to x times x. Actually, let me just I want to show a picture. And then there is our Simon's algorithm, where we don't actually do phase kickback. We still do the headmap to the n on our input register, and we do this weird measurement post-selection onto the record register. And there is a very complicated classical post-processing where you need to solve linear equation. We kind of just gloss over. And as a summary page, those are the algorithms we have. So George's algorithm want to answer where f equals 0, f of 0 equal to f of 1. And George-Josa want to ask whether f is balanced or constant. Bernstein-Vazirani, there is this hidden string s that you want to find, and the f of x is promised to be x times x, inner product with x. And then there is a Simon's algorithm. It's like collision finding, but with some structure. So the output are promised to have collision. So f of x equal to f of y if only if x equal to x plus y, o plus y. So this is addition in binary. And they want to also find this hidden string s. Okay. And then here are the quantum query and the classical deterministic query complexity, classical randomized query complexity, with the separation getting bigger and bigger. Well, yeah. Okay, and then two important things that probably going to happen in your midterm. Actually, yeah. So this phase kickback technique, if you understand. And then there is a nice computational formula that good to remember. That's when you apply headmap to the n on some computational state x, then you get equal superposition of all computational state, and we just change the variable name from x to z, and all those computational state will have the same absolute value weight. So absolute value of the amplitude are all 1 over square root n, so they have equal weight, but they have this plus 1 or minus 1 phase. Depends on the relation between x and z. And you get a plus 1 if x dot z equal to, so this is the inner product. So if x inner product with z is 0, then you get a plus 1 here, and x inner product with z is plus 1, you get a plus 1 here. Okay. So that's a quick review of our quantum algorithms. Any question? And I guess let's also do a review of things. Although we will do a more formal review next Monday, because midterm is next Thursday. And also there are these kind of questions. Where is it? Wait, okay, yeah. So there are also these kind of questions just ask you to calculate what happens if you have some input go through a circuit, what the output. And so I have a small summary here. So procedure that generally works is, or how we do this is, we write down the state at each time step in computational basis. This is also what we do when we analyze the algorithms, right? We look up like some of, let's see an example, sorry. We look up some of those time slices. And in general, we just write down all the classical information. So we write down the state at time slice in computational basis. And then we'll apply the gate onto the computational basis state. And here you want to do is be smarter. So when you apply the gate on the state, you want to look up the gate location, and you want to apply the gate in some kind of logical expression. And so when you apply the gate, then you know you are adding a -1 when a equal to 1, something like that. When the register you want to apply is 1, and you get a -1, otherwise you do nothing. And when you do C0, you do this kind of calculation. And when you apply head amount 0, it becomes plus. When you apply head amount 1, it can become minus. And this works because the gate we use all have pretty nice expression on computational basis. And and another way you can do this, and it's probably an exercise to try out it, but not very recommended when you are in an exam, is writing out everything as 2-to-n by 2-to-n matrix when you try to apply gate. So this is how we define things, so it's nice to try all this once or twice and see fundamentally things actually works. But as you might probably see in your homework, when you have about 3 or 4 more qubits in your algorithm, then when you write down everything in those 2-to-n by 2-to-n matrices, it's very likely you get like 8 by 8 or 16 by 16 matrix, and it's really, really painful to do that. So it works, but it will take a lot of time. So I guess if you are writing a computer algorithm, then this works. But if you are doing this by hand, then you need to consider whether this is efficient. Okay, any question on this chapter? Otherwise, let's go to this weird chapter where mostly for quantum universality, but also talks a little more about quantum circuits. So, okay, so let's go into this new chapter. The title is quantum universality, but we start with these principles about quantum circuits that we kind of omitted. Okay, so the first part is these measurement principles. And the zeroth principle, so this we already talked about. That is, we can assume all the measurement is in computational basis, and we have said this. So whenever we write down the measurement symbol, it's in computational basis. And this doesn't change the possible computational power, because we will prove this in the first or second chapter, that whatever general measurement, okay, so for general measurement is, let me write this. Yeah. So the general measurement is decided by a set of operator n. Let me. Oh, what is it? Okay, yeah. Just wanted to write down this really simple. Okay. So just remember, for general measurement is defined by a set of measurement operator mi. That's the most general measurement. But prove that to do any kind of general measurement, you just need to so you have some state here, then you just need to add some ancilla initialize with 0, and you do some unitary that has relation with this m, and you do computational basis measurement on your ancilla, and that will have the same effect of doing those mi. So computationally, it's easier to see what we mean. So what we mean by deferred end measurement is if you do a measurement before the circuit end, then maybe you can do something like this, right? You can have an adaptive circuit. So you can do a measurement here, and you will get, so the computational basis, so you will get 0, 1 here. And then you use 0 and 1 to do some classical control on your quantum gate, right? This is totally something you can do. You can have this adaptivity. So you do measurement here, then if it's 0, then you don't do this X gate, and if it's 1, you apply this X gate. And what do we mean by defer measurement? Okay, so now the question is, if you don't do this measurement here, because you want to defer the measurement at the end, right? So if you don't do this measurement, then how do you control this X gate to apply it or not? And what we can do is we can do this circuit instead. So instead of this measurement and classical control, we can do this quantum control. So we just do a C0 gate here. Okay? So now this whole part is a quantum control NOT gate. And you can do some calculation to actually check, but hopefully this is pretty intuitive, that this circuit actually has the same result as this circuit. So whatever you have a psi here, and you get a phi here, then you get the same psi here, you will get the same phi here. And actually this result, so you will get a 0, 1 here, and the 0, 1 will also have the same probability of 0, 1 here. So these two circuits are equivalent. And we don't do formal proof, but hopefully it's pretty easy to see. You can just decompose everything. Computational basis is 0. It's a 0 knowing because there is entanglement. So you probably want to write this psi equal to 0 plus some psi 0 and 1 times some psi 1, and let's be so nice and like A and B here, and you can see like the probability here of getting 1, 0 is A squared, and the probability of getting 1 is B squared. Same here, and then etc. But anyway, that's the principle of deferred measurement. So here is just one example, and you can see that if you are not controlling X, you are controlling some other unitary, then you just put control unitary here. Okay. So whatever this kind of classical adaptive measurement, adaptive control you put, you can also just put a quantum control gate here and do a measurement at the end. So that tells us, so this justifies something we said, but we didn't totally justify. That is, we say the measurement always happens at the end of the quantum circuit, and this is why. Okay. Question? Okay. That's a nice principle. And so this kind of principle, sometimes you think, okay, they are very easy, but I don't know, they are nice to, they are also nice when you do theory, because you know this kind of equivalence, then you can think about them back and forth, and your theory might be easier to think, might be easier to prove if you write a circuit in this term, or it's easier to prove when you write a circuit in this term. So it's also nice to be familiar with this kind of principle because you can view things in different angles and go back and forth and find an easier angle to understand things. But anyway, so that's the first principle, and the second principle is this principle of implicit measurement. And we already see this in Simon's algorithm. And okay, so the principle is a little dumb. So we have a picture here. What we want to say is we want to run a circuit, and the circuit is ununitary, and at the end you will do a measurement up here, right? Say you only need a measurement up here to get your outcome, so you get some outcome up here, some p string, 0, 1, 0, 1, 1, 1, something. And what this principle says is, well, this qubit that you don't need to measure, you can also measure them. Okay. So that's it. But as we already see in Simon's algorithm, this actually makes your analysis of your algorithm easier, because you can kind of say, well, I can measure it, and you get some measurement result, and you can post-select on the measurement result, right? So you can go through the measurement result one by one, and that will. So after you condition, so remember, say like in the Simon's algorithm. Let's see, Simon's algorithm. Simon's algorithm, we do this, and so it's this start step here. We say the measurement result is on D, so we condition on the measurement result is on D here. Then we'll project the state up here to something very simple, right? So we have this weird formula, and after we condition on measurement result D, then the first qubit of our first few registers is just x plus s state. Okay. So this can be also useful in analysis. And anyway, so for the proof of this, we kind of hand wavy over, but we did mention this when we talk about the reduced density matrix, right? So basically what happened is the upper register and the lower registers, they don't have any more interaction. That's important. If you want to apply this, then you need to make sure those are actually left over, they don't interact with other things more. So if those are left over, then this is a very fixed principle, because the qubits here and the qubits there can be actually physically very far away. So you will feel that you measuring those very far away qubits should not affect the the upper qubit. And you can also do this mathematically and prove that you think about the reduced density matrix up here, and find out that you're doing a measurement on the other part, then affect the reduced density matrix up here. Okay. So, question on this principle? And this is, okay. Personally, I think this seems very easy, but actually very useful in analysis, as we already seen in Simon's algorithm. And you can, later we are going to see Shor's algorithm, although I'm not sure. So Shor's algorithm can be also analyzed in a similar way, but I'm not sure we'll do it that way. But yeah, it can be also used to analyze Shor's algorithm, and that's pretty interesting. Okay, so those are the principles. So 0, 1, 2, about how to think about the measurements in quantum circuit. Okay, be placed in the end, and you can think about you measure all of them, something like that. And you can think about our in computational basis. Okay, then let's start this talk about quantum universality. So we already seen this slide, and so a short version is that there are 3 sets of quantum universality. The first one is CNOT and O 1 qubit unitary. And then we showed that you can use Hadamard and T-gate to simulate O 1 qubit unitary. And so those two are covered in the book. And we will so here we have a short version, and we will do a slightly longer version probably this week. But as we said, don't want to go into a full detail because it's a little too much detail. And also there is Toffoli and Hadamard is also universal, although it only do for real unitary. And one thing more to emphasize again in this short slide is that the CNOT and O 1 qubit unitary is the exact universal set. So that means whatever circuit unitary you want to apply, you can build from CNOT and 1 qubit unitary exactly. But for the CNOT, Hadamard, and T, simply because this is a countable set, so you cannot build every unitary exactly. So this is a approximation here. Okay? So you are basically approximating 1 qubit unitary with Hadamard and T, and this is called Solovay-Kitaev's theorem. Okay. And okay, so actually prove this is a bit too much detail, but there are some nice mathematics about quantum gate that we should talk about. So let's see this carefully. So it's nice to know this, even if you don't care too much about quantum universality. And it's this operator function for diagonalizable matrix. Okay. So first thing we want to talk about is this defining a function on matrices. Okay. So everyone know functions. So we think about a complex function. So function from some complex number to complex number. There are a lot of them. Like f of x equal to some number times x, or f of x equal to exponential x times some number. And then we want to extend this function onto matrices. And so how we define that? Well, here we give all how we define it. So assume our matrices is diagonalizable. Okay. So like this. So there are lots of ways to generalize it, but for diagonalizable function, for diagonalizable matrices, very natural generalization is, so this function, you just apply it on the eigenvalues of your matrices. So your diagonalizable matrix A has eigenvalue lambda and the eigenvectors psi lambda. Then you apply a function on your matrices. Then you just so then you still have the same eigenvectors, but you apply the function on all the eigenvalues. Okay. So here we see some example. So very diagonal matrix, very diagonalizable matrix z, right? So z is plus 1 eigenvalue, and with eigenvector 0 and minus 1 eigenvalue with eigenvector 1. And you see in the standard 0, 1 basis is already in this diagonal form, 1 and minus 1. Then let's think about the first function, f of x equal to just some number theta times x. We use this theta because we were going to see a reason later. But anyway, so if you think about f of x is just a linear function, you times whatever value with some real complex number theta, theta z. And as we said, then you multiply your eigenvalues with the theta. So 1 becomes theta and the minus 1 becomes minus theta. And in a diagonal form, you look at this. So it's 1 becomes theta and the minus 1 becomes minus theta. And you can also do a more complicated function. Let's say f of x equal to exponential of x and also times this theta. Then e to the theta z. Well, then what is e to the theta z function? Then it's minus 1. So there is plus 1 become e to the theta times 1. So it's e to the theta. And it's minus 1 become e to the theta times minus 1. So e to the minus theta. Okay, and in diagonal form is e to the theta, e to the minus theta. So, any questions so far about functions on matrices? Okay. And then we start to give you, then there are these examples of why this definition makes sense. So let's say, what if your f of x equal to a squared? Okay. And so if you apply it on any matrix A, then, well, if you apply the formula, then it says it should be some lambda, and lambda should become lambda squared because f of x equal to a squared, and your projector psi lambda. And they're actually equal to a squared, and there are several ways to see this. So one way to see this is because remember those psi lambda in our definition of diagonalizable, those psi lambda should be also normal basis. And yeah, it's also normal. So when you multiply A together, then all the cross term cancel and you only get this lambda squared term. Another way to see this is in kind of algebra, more algebraic expression. So you say A equal to some unitary times diagonal matrix times unitary. Right? This is another way to see diagonalizing your matrix. Then A squared equal to u dagger. Then is u dagger will cancel each other. So that's u d squared and u dagger. And so that will be equal to this because this u and u dagger will give you same set of eigenvectors, and the d squared will correspond to those lambda squared. Okay. Question? Okay. So yeah. So now you see why this makes sense. In some sense, because let's say you apply this function of x squared, then you apply on matrix, it also equal to matrix x squared, and then you can make this more general. So you can, let's assume our function is nice, and you get a Taylor expansion on your function. Okay? So this is in calculus. Hopefully you remember. And yeah, so assume our function is nice, and you can write down your function as a polynomial. So sum over coefficient an and x to the nth power. Then you can do a similar thing to this f of x to x squared thing, right? So now you will apply your function on matrix. Then, excuse me. Then last thing is apply f on lambda, and then you can do Taylor expansion on this f of lambda. So it should be summation n, and lambda to the n. Now you switch the order of summation, as we always do. And now have this sum lambda and psi n. And just like this a squared example, this sum lambda and psi n is actually a to the nth power. And now look at this thing. This is like doing this is very similar to this, right? So you apply any function on your matrix A is same as doing this Taylor expansion. Taylor expansion of your function f. You can just do Taylor expansion of your function f and just do this calculation, but swap x with a, and you get the same result. So that's really nice. And this means that our definition is makes a lot of sense, because it seems natural of what should happen when you generalize the function to the matrices. You will do a very similar calculation on your matrix. Okay, any question on the definition? Okay, if not, then now let's talk about, oh, I didn't? Okay. Three operators that I think we leak a little bit about this. But anyway, so we define three actually family of operators, Rx theta, Ry theta, and Rz theta. So those are very physically motivated, because they actually correspond to a rotation about x-axis, rotation about y-axis, and a rotation about z-axis. Okay, and so I guess you can think about Bloch sphere. So we are thinking about some particle with a spin half, actually means a two-dimensional space. And so those Rx theta, Ry theta, and Rz theta corresponding to you rotate your particle along x-axis, y-axis, and z-axis with angle theta, and what will happen to the quantum state of your particle. And but there are physics proof that you can use to show that, well, this is actually what happened. But here, let's just accept that. So those Rx, Ry, and Rz is rotations, and I believe there are also what happens when you do rotation on Bloch sphere. You can check that yourself. But for now, let's just define them as those three operators. And here we use the operator function we just defined, right? So this x and the y and the z here, so those are the, okay, so I should say sigma x. But anyway, so this x is the poly x, and this y is the poly y, I guess, okay. And this z is the poly z. Okay. So it's not very obvious in this form, but those x, y, z are matrix, and theta is the real number. So theta is the rotation angle, so it should be from 0 to 2 pi. Yeah. So theta from 0 to 2 pi, actually, okay. And x, y, z is polymetric sigma x, sigma y, and sigma z. So those are operator function. Sorry, matrices functions. You apply this function of exponential something to your sigma x, sigma y, and sigma z. Okay. So the first three lines are definition. And then you can use this to you can use the definition up here to calculate what they are, and actually they can be simplified quite a bit. That's because the exponential has this nice structure. So this Euler formula, right? So in your calculus class, you learn that e to the I theta equal to cosine theta plus I sine theta. This is for real number theta. In your calculus class. And if you take more advanced class, you may be using about complex theta. But anyway, so we know this formula is true. And the reason it is true is because you can do this Taylor expansion on your exponential function. Remember, e to the x equal to summation n from 0 to infinity, x to the n power divided by n factorial. And then when you put this x equal to I theta, then you can group terms into, so you can group the even terms into cos theta and the odd term into I sine theta. And here we can do similar thing. Okay, so we're back to our exponentiate of poly matrices. And so there is a property of polymetrics we need to use. That is the all square equal to identity matrix. Okay, hopefully you remember that. This is because the eigenvalues are plus and minus 1, and then plus and minus 1 all square to plus 1. Okay. Oh, excuse me. And okay, so assuming your matrix has square to identity, the exponential I a and some number x equal to, you plug in this formula, we just prove that you can do this Taylor expansion. So you do the same Taylor expansion with summation of the n and n factorial, and now this x to the n becomes I a x to the n. So nothing happened yet, we just use the Taylor expansion we proved. And then we do the even term and odd term grouping that we say we want to do. So what happened to even terms here? So there are a whole bunch of numbers, so the number is going to be n factorial and ix to n. And what about matrix part? So matrix part, you have a to the some even power, but you know a squared into the identity, so this is just identity to some power is still identity. Right? So those are even terms, and odd terms. So numbers are similar if you just write in symbol, but here you have the odd number of a. Okay? So maybe you have a, and you know 2a basically cancel each other because a squared into identity. So you are always going to left with 1a here. Okay. and now finally you deal with, so you see that the matrix part actually doesn't depend on the n, right? So the matrix part is just identity if it's even, and a if it's odd. And for the other part, then it's just the same calculation of this Euler formula e to I theta equal to cosine theta plus I sine theta. So let's just recall that. Let's just use the result from calculus, and you know this should be cosine, and this should be I sine cosine x, and this should be I sine x. Okay. Any question? Hopefully everyone get this review on calculus. Okay, so we have this. Then those three formula are very simple. So you basically do this, but with x equal to minus theta over 2. Right? So cosine minus theta over 2 is cosine theta over 2, and I minus theta over 2 is minus sine theta over 2. So that's why you get cosine theta over 2 here, and minus sine theta over 2 here. And xyz is just xa. Okay. And then you can write in matrices. Then for x and y, because x and y are off diagonal, so they're off diagonal here. And for their diagonal, they both have this cosine theta over 2, cosine theta over 2. And see the off diagonal here is minus I. Okay, yeah, because x is 1, 1 here, so it's just minus I here. But y is minus I and I, so you get some different thing here. And for z, z is also diagonal. So we actually combine the cosine theta over 2 and the I sine theta over 2 together into those exponential ones again. You can do that. Just use the Euler formula. Okay. And you can also see this. So we can also do some kind of check here. So you see that this is saying us what happened if we just use this kind of formula, right? Because z is already diagonal, so we can do this kind of calculation. So now z is already diagonal in 1 and minus 1. And you put 1 here, then you get this e to the minus I theta over 2, and minus 1 here, you get this e to the plus I theta over 2. So that checks out, we didn't make a mistake. Okay. Okay, so we have 4 minutes left. So we finished the part we want to talk about carefully. So let's see what we can do in 4 minutes about the really fast part. Okay, so now starting the very fast part. We want to decomposing things. So first is we want to decompose single cubic unitary into rotations. And this is the kind of decomposition we want to do. So U is any single cubic unitary. And there's a proof that we will not go over that any single cubic unitary can be done with this rotation on Z